Hello, this is Gaylord at SKG Automation. This video is about the SKG model 3613 single layer capacitor test fixture. For the last year, I have been looking into the fixtures that are available for testing SLCs. Mostly I find handheld probes or commercial fixtures that have been modified to test the SLCs. These can be made to work for physically large chips and for high cap value SLCs. However, handheld probes are difficult to use on very small chips and also on low value tight tolerance chips. Additionally, operators are much more prone to scratch the surface of the chip when using handheld probes. Modified commercial fixtures can be better than handheld probes, but due to limitations in precision, they are still a poor choice for low-value, tight-tolerance chips. For the same reason, they are also not well suited for lot qualification or adjusting the cutting dimensions to ensure that the lot hits the target value. One important issue is ensuring a repeatable open compensation. This is much more difficult when multiple operators are involved. Many operators attempt to set the gap between electrodes using shims, but due to precision limitations, this is a poor choice when dealing with low-value, tight-tolerance parts. A second issue is controlling the physical environment in which the chip is tested. For example, some fixtures have electrodes that are far larger than the chips being tested, so a very small change in the position of the electrode can cause large changes in the measured value of the chip. The model 3613 is designed to address and correct all these deficiencies. Let's look at the construction of the fixture. The base is very stable and weighs about 1 kilogram, and the vertical mounting plate is extremely rigid. Model 3613 has 2 linear rails and ball bearing carriages. The upper one, or the larger one here, is for moving the entire test head up and down. The smaller one here is for giving the upper electrode compliance. In other words, it's spring-loaded. This helps reduce or eliminate cosmetic damage to the chip surface. The contact here is designed to provide almost complete shielding of the upper electrode here. Only the exposed part is not completely shielded. The tip of the upper electrode is about 0.5 millimeter in diameter. It's made of a very hard, heat-treated, highly conductive alloy. The lower electrode is mechanically stable. It has a silver-plated copper surface. The spring-loaded push paddle is designed to push the electrode down so it contacts the device under test. The operator pushes the paddle up to break contact with the chip. This ensures a repeatable pressure is applied to the DUT. This plastic part is adjustable in the y-axis, and it is designed to form a datum to help locate the device under test under the upper electrode. The height adjustment screw here has fine pitch threads and allows very precise Z-axis movement of the upper contact. The small thumb screw here is used to lock the Z-axis position of the upper contact. The digital indicator here allows repeatable setting of the upper contact in the Z-axis to within 0.01 millimeter or 0.0005 inches. This degree of precision is not possible using shims and multiple operators. Two of the coaxial cables are attached to the upper contact here. These cables. There's extensive strain relief here and again here. The other two coaxial cables are routed under the base plate here. They are connected to the lower fixed electrode through a via. There's also extensive strain relief here and here. There are rubber bumpers on the bottom of the fixture base. The front bumpers elevate the fixture to make it easier for the operator to see the device under test. Open and short compensation is accomplished in the usual way. The difference is that you now have a tool, the digital indicator, that will enable adjusting the upper electrode with the precision of 0.01 millimeter or 0.0005 inches. Using the digital indicator as a tool, one can write a procedure that specifies in detail the open and short compensation process that all operators must follow, a standard procedure that will take a lot of the variability out of the testing process. We recommend that you develop a detailed open and short procedure that takes advantage of the digital indicator and also meets the particular needs at your facility. Publish the procedure and require all operators to use it. With the 3613 fixture, the short compensation value should be low and repeatable, usually around 30 or 35 milliohms. Open compensation using a 1 megahertz test frequency should be a low value and it should be stable. I mentioned earlier that the digital indicator is used as a precision tool to obtain open compensations that are repeatable. Following is a demonstration showing one way to perform the open and short compensation using the digital indicator. The meter is an Agilent 4980A, which is set for a 1 megahertz test frequency. Right now, the two fixture electrodes are not touching, so we get a small capacitance reading here on the meter. Using the Z-axis adjustment screw, I'm going to lower the upper electrode by turning it counterclockwise until it touches the lower electrode. The meter will present an overload condition when they touch. Carefully adjust the Z-axis adjustment screw until overload is just indicated, then push the 0 button on the indicator. Okay, there's the overload condition, and now I'm pushing 0, and that becomes your 0 point from which we will do our open and short compensations. First, I'll do the short, and I'll do that by lowering the upper contact an additional 0.010 of an inch, 10 milli-inches, and that'll be indicated on the digital indicator. So there's 10 milli-inches, and we see the overload condition, which means the contacts are touching each other. So now we have a way to control the pressure that's applied between the upper contact and the lower contact for short compensation. We can control it, and therefore we can make it consistent. So I'll now do a short compensation, and you see that the value of the short compensation is 36 milliohms, and that's usually pretty consistent. Next, we're going to rotate the Z-axis adjustment screw clockwise until we have an opening between the upper and lower electrodes of 7.5 milli-inches, and I'm picking that number because it might be typical of the sort of number you would use when you're doing an open compensation for typical single layer capacitor chips. Okay, so back through our 0, and we're going to set the digital indicator to 7.5 milliinches. So now the gap between the upper electrode and the lower electrode is 7.5 milliinches, and that's very repeatable to 0.0005 milliinches. I'll do the open compensation. And we have a low value, 0.171 picofarads, and you see the compensated reading is close to 0. And now we're ready to start testing chips. The short compensation's done, the open compensation's done, and the distance between the electrode is set. So we're ready to go. Earlier today, I measured 10 consecutive open compensations and recorded the value of the capacitance used for the compensation. These values are in this column here, and the units are picofarads. I then took the maximum of the 10 readings, and that was this one here, and then the minimum of the 10 readings, that was here. The difference between the maximum and the minimum is this number, which is 2.5 femtofarads, 0.025 picofarads. Standard deviation of the 10 measurements is here, 0.00838 picofarads. So this shows you that with taking some care with using the digital indicator and the Z-axis adjustment screw, you too can make very precise open compensations, and that leads you to very precise testing of your low-value, tight-tolerance chips. So you're looking at a single-layer chip that's been magnified quite a bit with a digital microscope, and we're looking at the image of the chip on a computer monitor, and you can see the chip looks pretty clean on the surface. What I'm going to do is transfer this chip over to the fixture and then measure it a couple of times and show you the measurements. And then I'm going to bring the chip back over to the digital microscope and we'll look at the surface and see how it looks after being measured. So bear with me a moment while I move the chip. Okay, the chip is now on the fixture, and I'm going to take my tweezers and move the chip underneath the electrode. We'll lower it. We get our measurement now. It's 1.179 nanofarads. And then I raised it. We'll lower it again. 1.179 nanofarads. Next, I'm going to take this chip off of the fixture and put it under the digital microscope again. And we will look at the surface. And that's what it looks like after it's been contacted twice on the fixture. Surface looks completely unblemished to me. And that's what you can expect if you take care when you're using the fixture and measuring your chips. If you are a manufacturer of SLC chips and you want to improve your process by reducing cosmetic damage to chips, getting tighter control of the manufacturing process, and improving your capability to test small size and/or low value tight tolerance parts, think about the SKG Model 3613 test fixture. It can make a major improvement in your production and testing. SKG Automation has a worldwide sales and support network. The website is www.skgautomation.com, and the direct telephone number in the States is 760-533-1019. Thanks for watching.